Hello. Today's lesson is all about equations. I'm going to begin by talking about equations in general and what it means to be what we call a solution to an equation. Anne's going to follow me by defining what we call a linear equation, and she's going to give you a couple simple steps that you can use when you're trying to find solutions to linear equations. Candace is going to end the lesson today by combining these steps that Anne has shown you in her part of the lesson. So in my part of the lesson, I'm going to begin by discussing why we might write an equation. I'm then going to talk in a little bit of detail about the vocabulary of an equation. What is an equation? What is a solution to an equation? And I'm going to end my part of the lesson by talking about different types of equations. So the first question is, why might we write an equation? And I'm going to kind of try and motivate you by using an application problem where we might write an equation. Let's suppose that the cost of a cab ride in Newtown, Virginia is $2 per mile on top of an initial charge of $2.50. Let's make a table showing the cost of cab rides of length 3 miles, 4 miles, and 5 miles. So the relevant numbers in the description of this problem were that there was a $2.50 initial charge, and then we were charged $2 per mile after our initial charge. Notice that I've got a table that really communicates what it is that I'm going to find. I'm finding the cab ride cost. I'm going to find the cost measured in dollars based upon the distance traveled measured in miles. So the first number it asked us to use for distance was 3 miles. So the cost of the cab ride if we go 3 miles is going to be $2.50 plus our $2 per mile charged for 3 miles. Since my cost column already says that I'm measuring cost in terms of dollars, I don't need to write any sort of unit down, and I can communicate $2.50 with the simple number 2.5. $2.5 is $2.50. I need to add to this our $2 per mile charge that's being charged for 3 miles. 2 times 3 is 6, and when we add 6 to 2.5, we end up with 8.5. And this 8.5 is representing a cab ride cost of $8.50. If we travel 4 miles in the cab, the cost is going to be our $2.50 charge just for getting into the cab, plus we're going to have our $2 per mile charge applied for 4 miles. 2 times 4 is 8. You add 8 to 2.5 and you end up with 10.5. So a 4-mile cab ride costs $10.50. We go 5 miles, $2.50 initial charge plus $2 per mile applied for 5 miles. 2 times 5 is 10. Add that to 2.5. You get a cab ride cost of $12.50. So let's suppose that C, measured in dollars, is the cost of the cab ride, and D, measured in miles, is the length of the cab ride. What is a formula for the cost of the cab ride? Before I write anything into my table here, I do want to note that I have different letter cases for C and D, and you do want to get into the habit that when you are copying letters from a word problem into your work, you want to make sure you use the same letter case. So the letter case for our distance was lowercase. We have a lowercase d representing the distance traveled. Looking at the 3 calculations I performed, I see they have commonalities. In all 3 cases, the cost started off with our $2.50 initial charge. So our formula is going to start with 2.5. Also, in all 3 cases, I added to this 2 times the distance traveled. When the distance was 3, I added 2 times 3. When the distance was 4, I added 2 times 4, etc. So when the distance is d, I need to add 2 times d. And this gives us our cost, which is a capital letter C. Now let's ask ourselves a different question. how long was the cab ride if the cost of the cab ride was $11.30? And to answer this question, let's assume that the fare increases every 10th of a mile. Well, looking at the numbers in my table, I see that the cost of a 4-mile cab ride was $10.50, and the cost of a 5-mile cab ride was $12.50. So it seems intuitive to me that if the cab ride costs $11.30, the distance we traveled in the cab ride must be somewhere between 4 miles and 5 miles. Also, if I think about this a little bit more, 11.3 is a little bit closer to 10.5 than it is to 12.5. So again, I would expect if the cost of the cab ride was $11.30, that the distance traveled is probably closer to 4 miles than 5 miles. Now I'm going to use what we call the guess and check method to figure out how long this cab ride was. I'm going to start a new table, and what I'm going to do with this table is I'm just going to guess different distances. Now the problem said assume that the fare goes up every 10th of a mile, so I think I only need to guess distances that end in even tenths. And I remember thinking that the distance is probably closer to 4 miles than 5 miles, so for my first guess, I'm going to guess 4.3 miles. So if the distance traveled in the cab was 4.3 miles, the cost is going to be our $2.50 initial charge plus our $2 per mile charge applied for 4.3 miles. 2 times 4.3 is 8.6, and when we add 8.6 to 2.5, we get 11.1. Now we're not aiming for 11.1. We're aiming for 11.3, so we don't have our distance yet, but we're really close. And you know what? I would bet you that $11.30 cab fare that the distance is going to turn out to be 4.4 miles. If we make the distance 4.4 miles, the cost is going to be our $2.50 initial charge plus 2 times the distance traveled, which is now 4.4 miles. 4.4 times 2 is 8.8, and when we add 8.8 to 2.5, we, yes indeedy doodle, get 11.3, so the distance traveled, yes, was 4.4 miles. But remember, this is an applied problem, so we're not done yet, because anytime you're asked for a conclusion in an applied problem, you need to write a complete sentence. So the question was, how long was the cab ride if the cost for the ride was $11.30? So if the cab ride cost was $11.30, the cab ride distance must have been 4.4 miles. Now this may not be the most eloquent sentence you've ever seen written, so it's a good thing that this is math class and not writing class. Just as long as we have a complete sentence that clearly communicates our conclusion, we're fine. Now I'm going to think about this question we were asked in a slightly different perspective. The question was, how long was the cab ride if the cost for the ride was $11.30? Recall that we came up with a formula for the cost of the cab ride. The cost of the cab ride, C, equaled 2.5 plus 2D, where D was the distance traveled in the cab. This formula is called an equation. And what makes this formula an equation is 2 things. 1 is the presence of an equal sign, and 2, there's a legitimate mathematical expression on either side of the equal sign. But usually when we use the word equation, we're talking about something a little more specific. And we can introduce this idea in the context of this applied problem. If the cost of the cab ride always equals 2.5 plus 2d, we can rephrase the question, how long was the cab ride, if the cost for the cab ride was $11.30, by writing down the equation 2.5 plus 2d equals 11.3. This is what we call a conditional equation. It's called conditional because sometimes if we replace d with a number, 2.5 plus 2d does equal 11.3. And sometimes when we replace d with a number, 2.5 plus 2d doesn't equal 11.3. For example, if we replace d with 0, 2 times 0 is 0, and when you add 0 to 2.5, you do not get 11.3. So the language we use is we say that 0 is not a solution to this equation. However, we figured out using our guess and check method that if we replace d with 4.4, the formula 2.5 plus 2d does evaluate to 11.3. So the language we use is we say 4.4 is a solution to this equation. Now there was a whole lot of the use of the word language in that last example, so let's talk about the language. What is an equation? What is a solution to an equation? An equation is a mathematical statement that has two expressions separated by an equal sign. Sometimes people who aren't being real careful with their language will say something like this. The equation 2 plus 3x blah, 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 and the blah, blah, blah doesn't have the word equal in it. Look at these two words, equation, equal. An equation has an equal sign. So the expression 2 plus 3x is not an equation because there's no equal sign here. I could make this an equation if I took 2 plus 3x and said that it was equal to 7. Now we have two expressions separated by an equal sign. That's what makes an equation. There's something else that sometimes somebody might write down that would not be an equation. Something like this, 2x equals. This has an equal sign, but it's not an equation because in order for it to be an equation, there has to be two expressions separated by the equal sign. This is, in a sense, an incomplete phrase. 2x equals. George Washington was. You need to complete each of those phrases. A solution to an equation with a single variable is a number that, when substituted for the variable, produces the same value on either side of the equation. Let's explore this idea. Let's consider the equation 2x plus 7 equals 23. Is 3 a solution to the equation? Well, if x equals 3, then our expression 2 times x plus 7, this is called a variable expression because it has a variable in it, it will equal 2 times 3 plus 7. 2 times 3 is 6, and when we add 6 to 7, we get 13. 13 does not equal 23. When x equals 3, 2x plus 7 does not equal 23. So 3 is not a solution to the equation. Is 10 a solution to the equation? Well, if x equals 10, our variable expression, 2 times x plus 7, is 2 times 10 plus 7. 2 times 10 is 20. Add 7 to that, and you get 27. When x equals 10, 2x plus 7 does not equal 23. So 10 is not a solution to the equation. Now, you're probably getting tired of seeing numbers that aren't solutions to the equation, so let's see if we can find a number that is a solution to the equation. Well, we already saw that when we replace x with 3, the variable expression 2x plus 7 evaluates to 13. And when we replace x with 10, the variable expression 2x plus 7 evaluates to 27. We want to find a value of x that makes this variable expression evaluate to 23. 23 is between 13 and 27, so I bet this mystery value of x is somewhere between 3 and 10. And 23 is a lot closer to 27 than 13, so I bet our mystery value of x is closer to 10 than it is to 3. So I'm going to try my guess and check method, but I'm not going to just guess wildly. I'm going to start with numbers close to 10 until I stumble upon the proper value. So let's try 7. If x equals 7, then our variable expression, 2x plus 7, is 2 times 7 plus 7. 2 times 7 is 14. 14 and 7 is 21. I don't want to get 21. I want to get 23. I don't need to write any kind of conclusion down here because I wasn't asked, is 7 a solution? I'm just kind of doing some figuring work to try and stumble upon a solution. So let's try another number. 7 was too small. Let's try 8. So if x equals 8, then our variable expression, 2 times x plus 7, is 2 times 8 plus 7. 2 times 8 is 16. Add 7 to that, and voila, we get 23. When x equals 8, our variable expression, 2x plus 7, equals 23. Therefore, 8 is a solution to the equation. Let's consider this equation. 2t squared equals 14 minus 3t. Let's substitute natural numbers for t until we find a solution to the equation. Remember, natural numbers are also called counting numbers, 1, 2, 3, 4. So I'm going to begin with a t value of 1. So let's suppose what happens if t is 1. This time I have variable expressions on both sides of the equal sign. So I'm going to have to evaluate both sides of the equal sign. If t is 1, then the expression on the left side of the equal sign, 2 times t squared, becomes 2 times 1 squared. 1 squared is 1. 1 times 2 is 2. And the expression on the right side of the equal sign, which is 14 minus 3t, becomes 14 minus 3 times 1. 3 times 1 is 3. Take that from 14, you end up with 11. 11 does not equal 2, so a t value of 1 is not a solution. What if t is 2? If t is 2, then the expression on the left, which is 2 times t squared, becomes 2 times 2 squared. Since powers are performed before multiplication, the first thing I need to do is square 2. That gives me 4. When I multiply that by 2, I end up with 8. And if t is 2, the expression on the right, 14 minus 3t, becomes 14 minus 3 times 2. 3 times 2 is 6. Take 6 from 14, and good for us, we get 8. When t is 2, both expressions in our equation evaluate to 8, so 2 is a solution. A solution to this equation is the number 2. it turns out that 2 is not the only solution to this equation. Let's show that negative 3.5 is also a solution to this equation. So again, I have a variable expression on both sides of my equal sign, so I'm going to have to evaluate both of these expressions if t is negative 3.5. Now I could do this evaluation using this decimal, but I think this is a good opportunity to review my fraction arithmetic. 3.5 is 3.5. 3.5 as an improper fraction is 7/2. So rather than calculating using the decimal negative 3.5, I'm going to perform my calculations using the improper fraction negative 7/2. And I'm going to go ahead and draw myself something approximating a line to give me 2 work areas to do the evaluation for the expressions on either side of the equal sign. So if t is negative 3/2, then our left side expression, which is 2t squared, becomes 2 times the number negative 7/2 squared. Because of order of operation, the power needs to be done first. In the power, I'm multiplying negative 7/2 by negative 7/2. The product of 2 negative numbers results in a positive number. So thinking ahead, I know my result's going to be positive. Also thinking ahead, 7/2 times 7/2 is a fraction. So I'm going to go ahead and write that 2 as 2 over 1 because it will facilitate multiplying that by the fraction I get from squaring negative 7/2. Again, negative 7/2 is the same as, negative 7/2 squared is the same as 7/2 times 7/2 because 2 negatives multiplied to a positive. So when I square negative 7/2, I'm going to get 7 times 7 over 2 times 2. Now I can see that there's a common factor of 2 to the numerator and denominator, and if I pull out those common factors, I leave behind my 2 factors of 7 in the numerator, and I leave behind 1 factor of 2 in the denominator. 2 over 2 is 1. Multiplying 1 by 7 times 7 over 2 just gives me my 49/2. Again, if t is negative 7/2, then our right side expression, which is 14 minus 3t, this becomes 14 minus 3 times negative 7/2. Again, I'm going to be thinking ahead here. I know when I multiply 3 times negative 7/2, I'm going to end up with a fraction that has a denominator of 2. So I'm going to go ahead and write 14 in a form that has a denominator of 2. 2 goes into 28 14 times, so written with a denominator of 2, 14 is equivalent to the expression 28 over 2. I need to subtract from this 3 times negative 7/2. When you multiply a fraction by a whole number, the numerator of the fraction needs to be multiplied by the whole number. So I'm going to get a fraction, and the numerator is going to be 3 times negative 7, which is negative 21, and this is happening over our denominator of 2. I have a common denominator of 2, so I can go ahead and perform the numerator arithmetic over this common denominator of 2. 28 minus negative 21 is the same as 28 plus positive 21. 28 and 21 is 49. This is happening over a denominator of 2. And yes, indeed, when I replace t with negative 7/2, the expression on the left side of my equation and the expression on the right side of my equation evaluate to the same number, specifically 49/2. So I can go ahead and say that since 2t squared equals 14 minus 3t when t equals negative 3.5, which in turn equals negative 7/2, that we can say that negative 3.5 is a solution to the equation. Now, you're probably thinking, how on earth would I have ever guessed that negative 3.5 is a solution to this equation? And the answer is, unless you've got some kind of power that I don't have, you wouldn't have ever guessed that negative 3.5 is a solution to this equation. So throughout Math 60 and any future math class that you take, one of the things you're going to spend a lot of time talking about is methods that you can use to find solutions to equations. In fact, you're going to get your first few methods in a later part of today's lesson. All right, let's talk about different types of equations. Some equations have no solution. For example, x equals x plus 2. What number can you add 2 to and end up with the same number that you started with? There is no number you can add 2 to and end up with the same number you started with. If you start with 5 and you add 2 to it, you don't have 5 anymore. You have 7. Anytime you add 2 to a number, you do not have the number you started with. Equations that have no solution, they're called contradictions. So the equation x equals x plus 2 is an example of a contradiction. It turns out that there are equations for which every real number is a solution. For example, 2x equals x plus x. Let's think for a minute about the meaning of 2 times 5. 2 times 5 precisely means the sum of 5 and 5. And this property is true no matter what number x is replaced with. 2 times a number always equals a number plus itself. Equations for which every number is a solution, they're called identities. So the equation 2x equals x plus x is called an identity. Now these last two words that I introduced, contradiction and identity, those are words that you're not going to hear often enough to just naturally assimilate into your vocabulary. So you're going to want to make a conscious effort to memorize the meaning of those two words. It turns out that some equations have no variables. You've actually been writing down lots and lots of equations already that have no variables. 7 equals 5 plus 2. 7 is a mathematical expression. 5 plus 2 is a mathematical expression, and they're written on either side of an equal sign. That's all it takes to make an equation. 7 equals 5 plus 3. Again, 7, mathematical expression, 5 plus 3, mathematical expression, two mathematical expressions written on either side of an equal sign. Now you're probably thinking, you know what, 7 doesn't equal 5 plus 3. And you know what? You're right. So we say that this first equation is true, and the second equation is false. So reviewing our vocabulary, we could say that 7 equals 5 plus 2 is an identity because this statement is always true. And we could say that 7 equals 5 plus 3 is a contradiction because this statement is never true. It turns out that some equations act as formulas. Some of you may have seen the formula F equals 9/5 C plus 32. This is a formula that we use to convert temperatures. Specifically, if F is the temperature measured in Fahrenheit and C is the temperature measured in Celsius, we could easily use this formula to convert a Celsius temperature to a Fahrenheit temperature. For example, we could use this formula to convert 20 degrees Celsius to Fahrenheit. This is a problem it would be good for you to practice. I'm going to show you the solution for a few seconds, but I'm not going to really talk about it, so you might want to practice this on your own, and if you need some hints, you can look at this screen that shows us that if C is 20, after we do all of our substitutions in arithmetic, F turns out to be 68. So the Fahrenheit equivalent of 20 degrees Celsius is 68 degrees Fahrenheit. Notice that even though I flipped through those screens real fast, I just couldn't control myself. I had to have a complete sentence conclusion that clearly expresses what I was trying to find and what the result was. Most of the time when you hear the phrase equations, you're really talking about conditional equations. And conditional equations are things that we want to solve. When asked to solve an equation with a single variable, your objective is to find any and all values of the variable that result in the same number on either side of the equal sign. There's another way of saying that. When asked to solve an equation with a single variable, your objective is to find any and all values of the variable that make the equation true. What does it mean to be a true equation? Same number equals same number, that's true. Same number equals different number, that's false. That's what it means to be a true equation and not a true equation. Let's do one last example. Let's find the solution to the equation x minus 2 equals 17. In some earlier examples, I talked about the guess and check method. We don't really need to guess and check here, I don't think, because we can take this equation and translate it into words. From what number do you subtract 2 and end up with 17? Well, if nothing else, we can count backwards and figure this out. Let's see, 17, 18, 19. 19's the number that we subtract 2 from and end up with 17. When x equals 19, our variable expression, x minus 2, indeed equals 17. So 19 is the solution to the equation. Now, the reason I did this as my final example is because this is an example of something that we call a linear equation. This equation, x minus 2 equals 17, is an example of something we call a linear equation, and Anne's about to come up and start talking to you about linear equations.